Hey guys, so this is the first video for solving or upsolving the contest from Atcoder. So this is the contest 293, so I'll be discussing the problem A, B, C and D. Since the problem A and B are pretty easy, I'll try to rush them a bit. I hope you have solved them. If you're watching this video, if you haven't and you feel some problems in this, you can contact me on Discord or you can comment down below and I'll try to explain it over there itself. So let's get started with the problem A. So the problem A is swap odd and even. So what they're saying is that they have given you a string, right? You have to swap the alternative elements. So I'm not going through the exact problem statement because I've already read it, but you just have to swap the alternative elements. So for this particular string, you'll swap A and B, that would become B and A. Then you'll swap C and D, that would become D and C. Then you'll swap F and D, then that will become so you'll swap E and F, that will become F and D, right? So this would be output. This is a pretty straightforward code. All you have to do is that you had to take the string first, and then for every two consecutive indices you just had to swap them and then print the string. So yeah, this is the working code for it. I don't think this actually needs a more like elaborate discussion. This is a pretty standard and pretty easy question, right? But definitely if you have doubt you can let me know. Cool, let's move on to the second problem. So the second problem is call the id number. The problem states that there are n people whose ids are from 1 to n. Each of the person from 1 to n performs the following action once in this order. So if now this is a important statement that needs to be considered. So if the person i's id has not been called out yet, then call out the ai's person id. Cool. So that means that if I'm a person x, right, and if I have not already been called, then I can call the person that I'm supposed to call. Now what do I mean by that? So for example, this is the place of the first person, and the first person is supposed to call the person 3. Now in the beginning itself no one is called, so the first person would say that okay, I have not been called, so I'll call the person 3. That's fine. Then I'll move to the second index. So the person at the second index, he also is not called right now, so he'll say that okay, I'm not called, so I can call the person at the location 1, or I can call the person 1. That's fine. Then we'll come over here. So this is the person at third index. Now the person has the person at the third index has already been called. He was called by the person who was at the first index. So when we'll reach here, he'll say that okay, I was already called, so I cannot call the other person or the person I was supposed to call. So 3 was actually supposed to call 4, but since 3 was already called, hence he cannot call 4. Then we'll come to 4 itself. He'll say that I have not been called, so I can call the person you want me to call. So we want 4 to call the person 5. He'll do that. Then we'll come at this index. So this is the person 5. He'll say that okay, I was already called, so I cannot make a new call now. And after that we have to tell them the number of indices that were not called, right? So over here we can see that okay, person 3 was called, person 1 was called. We weren't able to call person 4 at this point because this was the place of person 3 and person 3 was already called, right? So we weren't able to call person 4. Then we called person 5 as well. Then we came over here and then we were not able to again call person 4. So in total we are not able to call person 2 because person 2 is not at all called anywhere. And we were also not able to call 4, although 4 should have been contacted twice, but the people that were supposed to call person 4 were already contacted, right? So yeah, that's what we need to print. So we need to print the count of those people and then those people. Cool, let's look at the code. The code is also easy. So what I'm doing is firstly I'll take the people or this. Okay, so this is the array in which it basically represents the person at the ith location. So let's call it p of I or p of I. This basically represents the person ith person would call, right? Okay, so then I'll take this another map. So this is just taken in order to get in order to know that what all people have already been called, right? I could have taken a boolean over here if I wanted, so I can do it in that form, but anyway it doesn't matter, so let it be. So what I'm going to do is for each of the indices I'm going to check if that particular index has not been called. So I could have done this. This would have also made sense. I don't know why I actually meant I actually used I equal to 0 over there, but anyways this would make sense. So if I have not been contacted, right, now I'm taking I plus 1 over here because they are talking of 1 base indexing and by default the things we are storing are stored in 0 base indexing, right? So I'm taking I plus 1. If this person wasn't contacted, then it can contact the person it was supposed to. So if my person at the ith location wasn't contacted, ith person wasn't contacted yet, then contact the person a of I. Cool. That's what I'm doing over here. Then after I performed this, then I'll need to know that what all people have not been contacted, right? So I'll go from 1 to n. I'll check what all, if that particular person has been contacted or not, right? So I'm not using a not has been contacted. So if it has not been contacted, then I need to mention it in my answer. So I'll put it in my result. Now result is a set. Now the only reason for taking a set is because set contains the values in a sorted order, and we wanted that the value and the question explicitly states that the answer should be in a sorted fashion. Okay. Okay, yeah. So they over here they state that it should be in ascending order. So that's why I'm taking a set over here. I'll firstly print the size of the set that will denote the number of people not contacted, and and then the people who were not contacted that would be present in my result set. Cool. So that was it, and it's working for the sample test cases. Let's move on to problem C. Problem C is a pretty typical and a pretty easy problem. Now you can call it a DP problem or a graph problem. I'll just call it a recursive problem because we don't need to save the states given the constraint. We don't need to save the states or anything like that. So problem C is that there is a grid with height h horizontal rows and w vertical columns. So there's a grid like this. So you have a square box wherein you have h horizontal rows and w vertical columns for two integers I and j, such that I is less than equal to h and j is less than equal to w. Obviously their lower bound is 1. The square at the ith row from the top and the jth column from the left is not what this is. That's pretty standard. And now Takahashi is that the very first column or the top leftmost column. So she or he would be actually over here. And what they want to do is that they want to reach over here. Cool. The only constraint is that when you are traversing this particular matrix, now let's say I go from A11 to A22 then to A23. So I can only move downwards or to my right. There's no other direction I can move to. So whenever I'm going to these directions, the number I would be standing at, so let's say this was a 1, this is 2, this is 3, this is 4. Now I can go over here, but let's say this was a 1, this was maybe 5, this was again 1. So then this particular route from A11 to A21 and then to A22 won't be valid, because the cells I'm visiting should have unique values, right? That's the only constraint I need to follow. So I have to tell them that how many ways are there to reach AHW if the cells I'm visiting have a unique value itself. That's a pretty standard recursive call, or that's a pretty standard recursive algo. So what I can do is I can denote the function I'm going to use as DFS. You can denote it by any name you want. Over here, one thing you might not know is that how I'm taking this particular adjacency list. So I have actually defined, or I have predefined a template for that. So whenever I need to take a array, so I don't need not take it like element by element. I can directly use cin on the entire array because of this thing right over here. So this helps me to take the entire array in a single go, right? So firstly, I'm taking the adjacency list. After that, I'm calling out the DFS set, right? So what is passed on to my DFS is the current indices, that is the x and the y, or the ith and the j, where I represent the row and j represent the column. Then the agencies list, that's obvious, or the you can actually call it the matrix. This is not a list, that is the entire matrix. After that, I'm also passing a visited set. Now why I'm passing this? Because the constraint that I need to follow is that all the indices or indices being utilized need to be unique. Cool. So what I can say is that so I'll be getting the limits, that is n and m, right? Now if I am at a place wherein I have actually crossed the limits, so so my array limits goes from 0 to n minus 1, right? Considering zero based indexing, so 0 to n minus 1. So this is the range for the rows, and for the columns the range is 0 to m minus 1, right? So in case I'm having anything that is greater than or equal to n, or if my rows have become greater than n minus 1, or if my columns have become greater than m minus 1, then I can return a 0 because I'm currently standing at a wrong index, or I've actually gone out of bounds. So in that case, I can return a 0. If my x is n minus 1 and y is m minus 1, so that means I have reached the last index and that's exactly the place I wanted to reach, then return 1. But wait a second, I also need to check whether the index I'm standing on, if it's a valid index at all. Now what do I mean by valid? So I shouldn't have already processed this particular value in the route I was taking. So if this particular value that is given by the index at or the matrix value at that particular index, if that has already been seen, then I'll need to return a 0 because this is not a valid path. Else, if I've come over here, then I can say that, okay, insert this particular path or insert this particular value or this particular cell to the visited set. And then you have to go further, right? So in what directions can you move? So there are only two directions in which you can move. You can move to the right or you can move down. So if I move down, my row gets incremented. If I move right, my column gets incremented. So if I move down, I'll say x plus 1. If I move right, I'll say y plus 1 and I'll pass the things along. Right? Whatever sum I'll be getting for moving right and for moving left, I'll be returning that. But before returning that, I need to make this visited set valid. So right now I'll say that, okay, since I'm traversing back or because I'm going out of this recursive call, so I'll have to erase this particular element as well. I hope you already know how recursive calls work, right? So I need not explain this logic in detail. Yeah, so that was it for the question. And you just need to print at the end, you just need to print the value starting at 0, 0. Cool, I think this was easy enough. Now generally, if you are like not new to this channel, you might know that I actually explain the questions in detail on my iPad, but the thing is that these questions are pretty standard. So I didn't think there was a need of discussing this, but you can always let me know your views in the comment section so that I'm able to make better videos in the for the next contest. Let's look at problem D. This is a fine problem. I'll not say it's really tough, but it's fine. Okay, so the problem D states says that there are n ropes, number from 1 to n. One end of each rope is painted red and the other is painted blue. Now you have to perform M operations of tying the ropes. So they have given you the what the operations are. So in a single operation, you take a row A, right? Now for the row A, it could be painted red or blue, right? And then you'll also take a rope C. It can also be painted red or blue, right? Or like for each of the rows, one end is red and the other end is blue, right? So right now we'll take the rope A1 with a particular end. So they'll be saying that, okay, take the row A1 with the red end or the blue end. Take the rope C1, C or Ci with the red end or the blue end and tie them together. So that's what they are going to tell us. Now we're going to perform this operation again and again. So let's just take an example. So over here they say that, okay, take the rope 3, take the rope 5 and tie the red end of the rope 3 with the blue end of the rope 5, right? Then they say that, okay, tie the red end of the rope 5 with the blue end of the rope 3. Now this would become a cycle because this is, okay, let me explain this on the iPad. This probably would make more sense then. Okay, so this was my rope. Okay, yeah, this is my rope and this is my rope 3. This was my rope 5, right? Let me color it appropriately. Okay, so this is the red end, right? This is the blue end, and let's say this is the red end for this. Okay, this is the red end for this, and this is the blue end for this. Firstly, I ask you that tie the blue end of the rope 3 with the red end of the rope 5. So you actually tie this. So you tie this. Then I ask you that tie the blue end of the rope 5 with the red end of the rope 3. So you'll make a connection like this, right? Now this is technically forming a loop, right? So this is forming a cycle. I hope that makes sense to you. Now what they've asked is that you'll be performing these operations and after that you have to tell us that how many groups are there which actually form a cycle. Or so over here what would happen is that you'll be making you'll be having three groups after this. So this 3 and 5 will actually make a cycle, that's known. Now this 2 and 4 are also connected, right? The red end of the rope 4 is connected to the blue end of the rope 2, but they're not forming a cycle, they're just connected, right? So we'll say that, okay, 3 and 5 are connected and they're forming a cycle. 2 and 4 are connected, they're not forming a cycle. And 1 is a rope that is lying, but it's not connecting to anything else. So these are the sets we are having. Now over here 3 and 5 is the only thing that is making a cycle. So how many cycles do we have? We have one cycle. And how many other connected components we have? So the ropes which are actually which are over there connected to one another, but they're not forming cycles. So there are two pairs. One is of the 2f4 and one is a single one, right? So there are two sets that are not forming cycles. So that is what we have to print, the number of cycles and the number of remaining sets. So how would we do that? So now there are multiple ways of doing it. So actually, if you do it via queue, then the code would be a bit smaller, but I just wanted to show you the code that I wrote in the contest itself. Yes, I did optimize it a bit, but it's still in the pretty crude form that I actually submitted in the contest itself. So I'll be explaining this particular code itself. Cool. And so what we are doing is that I've made two adjacency lists. One is the R ADJ or the red end ADJ, and one is the B ADJ or the blue end ADJ, right? So red end ADJ basically means for the ith rope, so for the ith rope, have I connected the red end of this particular rope with any other rope? So that is what RADG means. And BADG means that have I connected the blue end of the rope I with some other rope. Cool. Then I'm given M connections in total. So I have to take the values. So I'll be taking the rope 1 and the end it's connected with. So CU actually would actually contain the colored end that I'm using of the rope U, and CV would contain the colored end that I'm using of the rope V. I'll be taking that. Then I'm gonna decrement my U and V. Then I'm gonna say that okay, if the current end of the rope U which you were considering is R, then I want to update my R ADG U with V. So I'm gonna say that okay, the rope so the red end of the rope U is connected to V. If that's not the case, then since there are only two possibilities, so it's gonna be blue, right? So I'm gonna say that the blue end of the rope U is connected with V. Similarly, I'm gonna do the same with V itself. So if the red end of V is connected, then I'll say that okay, the red end of the V is connected with you, else the blue end of V is connected with you. So that's what I'm gonna do over here. Then I'm gonna make a DFS call. Before doing that, I'll have to mark the visited array so that I don't recompute the things. So I'm gonna take a visited array or a visited boolean vector. I'm gonna take two variables. This is cycle and this is singles. Both are initially set to 0. Now for each of these indices, now I'm gonna check if they're forming cycles or if they're not forming cycles. So my DFS call actually returns me true or false based on the thing that if it's forming a cycle or not, right? So firstly, I'll check that if this particular rope, if it has already been visited. Now it would have been possible that okay, I already checked for rope 0 and 1. Now let's say 1 was already making a connection with 2, right? So it should have marked 2 as visited already so that I don't recompute it. Cool. So that's the motive of using visited. And now let's check the DFS call. So what I'm doing with the DFS call is as soon as I get to a node, I can actually call it rope rather. That would make more sense, I guess. Yeah. So as soon as I get to a rope, right, I mark it as visited. Then I check that if if the current index or the or the red end of this particular rope is not -1. Now why -1? Why I'm taking -1 over here? -1 is the default values. Now let's say for a particular rope, if one of its end is not connected, then its default value is going to be -1, right? Also, if you are trying to make a cycle, then technically both the ends of the rope would be connected, right? So that's what I'm checking over here. If it's not -1, and if the rope that is connected to the red end of it is already visited, and if the blue end is also not -1 and the rope connected to the blue end of it is also visited, then in that case I've already seen a cycle. So because in this particular case, the thing you will be having is something of that sort. So give me a second. Yeah. So the thing that this would signify is that let's say this is a rope, right? Now this is the, let's say the red end. This is the red end and this is the blue end, right? Now I'm saying that you are standing at this particular rope and you're able to visualize that the rope that is connected to the red end so the rope that is connected to the blue end as well as to the red end are both visited. What does that tell you? That since you would have, let's say you started a rope X, right? You came all the way over here. So you started a DFS call, you came over here, but now you see that this node is also, this rope has been visited. So that means there was a connection from here to here as well, right? Then only this rope would have been visited, right? So if this kind of a scenario is happening, then technically I'm having a cycle. That's obvious. So if this kind of a scenario is happening, return 1. Else what can happen is that your red rope is not -1, right? And when you check if it's so it's not -1, and also it is not visited yet, right? So what do? You'll definitely have to go for a DFS traversal. As soon as you'll be using a DFS, and if there's a cycle over there, now there could only be a cycle. Now, how do I prove it? Like I can prove it mathematically, but I just wanted to prove it graphically. Now the thing is that let's say this particular rope is connected to another rope like this, right? This is connected to some other rope. Now, if this rope tells me that I'm a part of a cycle, that technically means that this rope is also part of a cycle. Now, why is that the case? Because every rope just had two ends and they are just connected to one rope, right? So it cannot be the case that this rope's, let's say, red end is connected to two ropes. That's not going to be the case. So it cannot be this case, right? So this is not possible. So since this is not possible, if a particular rope says that I'm a part of a cycle, so I'd say that okay, I'm a part of a cycle. That means any node that is connected to me is also part of a cycle. That's obvious. So if it says I'm part of a cycle, that basically means there would have been some sort of a connection that would have gone all the way over here, right? Only in that case it could have been a part of a cycle. So if any one of my connections report that I'm a part of a cycle, so obviously I also would be a part of a cycle. So as soon as it returns that okay, I'm a part of a cycle, this would say that okay, I'm also part of a cycle, right? So that's what I'm doing over here. If it says that I'm a part of a cycle, I'll also return 1. So 1 basically means I am having a cycle. Right? Cool. Same I'll do for the blue end as well. Right? But if none of its neighbors or none of its connection report that they are part of a cycle, that means technically there's no cycle at all. So if that's the case, return 0. That's the thing I'm doing over here. Let's test it out. Okay, it's passed. Yeah, so this is the exact code I used in the contest too. So I hope this made sense. Now for the problem E, I haven't solved it, so I was using a different method. I can explain the math behind it if you want, but that would be a waste of time. So the thing is that there was a simple observation that the answer would always be a to the power x minus 1 divided by a minus 1. Now, how does it comes if you're able to represent any number, right? Let's say 2 to the power n, right? 2 to the power of n is actually equal to 1 plus summation of all the numbers from 2 to the power 0 plus so on to 2 to the power n minus 1. To generalize it, I can say that, okay, so what I can say is power of a to the power x, right? A to the power x is equal to a summation of all the numbers from a to the power 0 to a to the power x minus 1, right? And plus 1 over here. Now as you solve it, you'll get over here, get to this point. I hope that makes sense. So it would basically become a to the power x minus 1 divided by a minus 1. So as soon as you get it, then you'll try like the only problem over here was that a minus 1 was in the denominator. Now you have to get a modulus inverse of the same. Now getting the modulus inverse is always possible if and only if the thing you're trying to divide or the thing for which you're trying to take the modulus inverse, if that number and the modulus itself are co-prime. If they're not co-prime, then the modulus inverse doesn't exist actually. So that is the only reason why I was getting the wrong answer for some of the test cases. Although the base cases are passing, but it's going to give error. Now the actual way of solving it is pretty complicated. I don't think I'm the right person who can actually teach you that. So I won't be going that path. But anyway, I hope you were able to understand the problems A, B, C and D. From now on, I'll try to make regular video tutorials for these problems. Let me know if I can improve anything in my teaching. Cool guys, thanks a lot for watching this video. Bye bye.